Hello everyone, this is the third day and Eyüp is continue with his lecture on spin 7 geometry.
Hello and welcome for the third day of the lecture series about spin 7 geometry. And maybe I can mute another account. Okay. And today we will continue from the presentation letter. We finished the Jamboard part and just a few slides related to previous talk, and then we will continue with the real the hardcore part of the spin 7 geometry. So the overview is covered Octanian, and then calibrations and G structures, in 7 structure, Calabi-Yau manifolds, two-plane field, and at the end of the lecture we will cover the mirror duality on spin 7 manifolds. So we taught this classification before. You can remember this is the famous classification, and if your holonomy class is the for simply connected Riemannian manifolds, and these holonomy groups are irreducible and unsymmetric, we can start with in general the largest group is just the SON, and it's only the orientable manifold. But if you reduce your holonomy into SON, we know that all G in SON, or holonomy GSON, if you put in some extra condition for a structural group, you will find the UN, and it's named by the Kähler manifold. The properties about the curvature, it can be anything. But if again you can choose the special unitary group, and you can take the determinant of this UN is 1, you're forced to be in a Calabi-Yau manifold, and the properties are Ricci flat. Ricci flat means, roughly the curvature, the preserved. The Ricci flatness means the mean curvature of the manifold is roughly stable. So we can say that the Ricci flat metric, and this metric is very important in the general and the spatial relativity and the physical correspondence. And we mentioned this one is the quaternion Kähler and the hyperkähler. This is out of our talk, and the G2 and the spin 7 is the interrelated to each other, and the 8-dimensional and 7-dimensional object. We covered this one before. Now, the Octanian and the spin 7 relation is like this. Here, if you have a non-division algebra, we talked non-division algebra before, it has to preserve these property, the non-multiplication. It's nothing but so on this non-division algebra, we can look at that the automorphism group of these non-algebra, and if you are living in the real numbers, automorphism group is just identity. So there's no choice for your restriction. But if you choose the complex numbers, the complex numbers gives the Z2. We have two different automorphism, one sends to 1 and one sends to I. Okay. So for the automorphism group of SON, automorphism group of the quaternion, and it's the SO3 group, because I sends to J, one possibility, I sends to K one possibility, and I sends to I. So for three components turning around itself, and this is nothing but the SO3. So the other important case, and the automorphism group of octanion is the G2. So this is another definition of G2. So it's turning around E. Maybe we can say that E1, E2, send up to E7. So you construct the group and these 7 elements turning around itself. Okay. So maybe you can remember from the quaternion, I'm sorry, give me a second. You remember that from here, the kind of multiplication IJK. Okay, so the same multiplication I will write a little bit later. The same multiplication is preserved. The cross product, the new types of cross product is available on octanion. So for this cross product gives us the loss of rich structure and the rich geometry, and induced from here the automorphism group of octanion gives us the G2 group. So to be able to understand the spin 7 geometry, we need to understand the octanion. Here I gave this information yesterday. Norm division algebra, the positive definite metric, and it has to preserve this multiplicative property. And we gave yesterday the theorem is only non-division algebra is the real numbers defined on real, complex numbers, and also quaternion and octanion. Okay, are the only properties. Here we mentioned the octanions as induced from the non-algebra property. This is yesterday we talked that this is A plus and A plus also. So if you start with an A is the quaternion, so you can take the direct product and you can construct a new types of geometry. But here after the octanion, the 16 dimension, I wrote maybe yesterday or previous day the same thing. I mean, 16 dimensional object is the symmetric object, and the gray proved that. So for the higher dimension, somehow it can be reducible or the symmetric, and that's why I mean the octanion is the highest possible geometry to be able to use the non-division algebra. And this octanion is also another important property you can construct here is the cross product. Okay, cross product. Previously, maybe you remember from high school calculus somewhere, the first cross product you learned, you see is just the image of quaternion, right? IJK. And this cross product generalized, or we can add some of the new coordinates. We can define the new cross product in these spaces. So that's why this space is important. I mean, if you go further, one step further, again the gray prove that the vector cross product on manifold, probably the book names. Maybe I can write somewhere here. Gray vector cross product on manifolds. This article shows that the only cross product defined on the imaginary image of quaternion, image of octanion, and trivially the real number, maybe the determinant bundled directly, but it's not so big importance for us. And they show that only the non-classical example of cross product defined on the image of octanion and image of quaternion. That's very nice article, you can check. And this shows that octanion is useful for also the cross product. And so if you remember the octanion, so we yesterday construct the octanions as the direct product of the quaternion, and the multiplication here, AB times CD, can be written as if you want to multiply these sets, AC minus B bar and BA plus BC bar, and the inner product is like the standard one from here. And for this information, now we can say that octanion is a non-division algebra and induced from the quaternion information. Now, if we construct octanions, we can see octanions as a span of the real one unit elements of 1 and E1 to E7. So, but the important part that we need the information of this geometry, and this geometry can be written as the general element. We remember from yesterday, this is the real part, real of V, and this is the real, the imaginary parts of V, okay? If V is the octanion group, octanion vector space. And from here, the multiplication table defined like this, you know, again, I mean, there's lots of similarity between quaternion and octanion. E1 is -1, E2 minus 1 also, and but the rest is directly we have to memorize. I mean, or another triangle and circle way to memorize here. Kinds of this one, E1, E2, E3, okay, and E4, E5, E6, E7, and from here, E1 times E2 is gonna be E3, and E3 times E1. I mean, we can check to put the correct order, but more or less these triangles gives us the correct multiplication. If you remember from the quaternion directly, you can see, but we have two more base elements. And also from this construction, you can write that the quaternion elements is 1ijk, and from here we can construct the elements of octanion is as a basis element. Octanion is like this 1ijk, and now we need a new component L. So L, Li, Lj, and Lk. Okay. So if you define the multiplication for this new component, you can see directly it's the combination of H product with H. This is both constellation gives us the same result, but these two construction gives us an idea. From obtaining, you can study it with the two ways. One of them is it contains the quaternions plus quaternions. This is the two four-dimensional object, and from here you can see that somehow in the spin 7 geometry you can talk about that the four-dimensional submanifolds, and it gives us also the different meanings, different information here. And another way to be able to understand the octanions, we can look at the octanions as the real part and imaginary part, and from here you can see octanions in the complete block. There's no separate pieces. For that construction gives us the general idea and the full holonomy. Actually, if you divide the octanions into two pieces with a four-dimensional object, you reduce the holonomy actually. So that's maybe, I mean, not so complicated spaces, because you divide your octanions into two pieces. One of them is a quaternion, another one is a quaternion. So the quaternion also with geometry, and from this octanion you can get lots of richer geometry, because some of them induced from the quaternion directly. But if you look at that, the octanion with a 1 and 7 non-unit basis elements, so this construction gives us a general picture, and to be able to understand our picture is a little bit harder than the previous one. But both of them gives us the same result. And for the octanion construction, I said if the real part of the octanion is the span of 1 and image is span of E1 to E7, and it's maybe I can say something here that this image of octanion is the automorphism group of image octanion will give us the G2. So we say many times, but G2 and spin 7 are interrelated to each other. So this is also the automorphism group of octanion. Can be constructed by the image of octanion, and it fits the geometry of G2 directly. So for each element from octanion can be decomposed into two pieces, real parts and imaginary parts. And yesterday we showed that it's unique. Sorry. Okay, and the conjugation is the real parts minus imaginary parts, and so the real cases can be constructed with x plus x bar, imaginary parts x minus x bar, and here x maybe this is we want to check. I'm sorry, this one maybe has to be the big bar, and for identity, if your elements multiply right hand side, you can take it out with no. And previously we talked that the inner product can be written as the x times y bar, the real part of this one. Okay, and the last thing we covered yesterday, if they're orthogonal, we can switch x y bar equal to minus y x bar. Okay, and we know that the octanions are not associative. We lost that information from the Hurwitz theorem RC, the quaternion and octanion. For each step, we lost some information. Okay, the complex numbers has no order, and if you look at that, the quaternion, there's no commutativity here. Ij is not equal to ji, and if you're passing from here, you will lose the associativity. The one step further, nothing else. Okay? And this is another a nice idea. There's no higher dimension. And for the geometry of octanion is we think about that octanion the roughly equal to or isomorphic to R8, and for these spaces we have the triple cross product. I said the triple cross product, and actually cross product idea gives us the new vector orthogonal to these the three elements. Okay, let's say this is the chi, and chi is orthogonal to x, chi is orthogonal to y, chi is orthogonal to z. Okay, so this is the property of the cross product, and this cross product can be defined as the element of R8 again. How can we define this one? This cross product you can multiply with x, y bar, and multiply with z, subtract from z, y bar times x here. So, and from this part, this is actually the volume form, okay? X, y, and z. And another definition for the Cayley-4 form, we will see later the new definition. The Cayley-4 form can be constructed as x, y, z, the triple cross product, okay, taken inner product with V. So these four form, okay, for each element it's a vector. Actually, you can put a vector, so we can write that phi 0 is a Cayley form, Cayley-4 form, okay. So this form is a 4 form, and this 4 form is very important to construct spin 7 geometry. And here you can you can find an analogy. Actually, the Cayley form, if you know the J, okay, J is actually for each element from the real. If you go to I, this means that if you are living in the complex geometry, take each element sent to imaginary path. So it's just actually the rotation with a 9 pi/2 degree. Okay, so this geometry, the octanion geometry, is the analog of the complex and the Cayley geometry. If you have the Cayley-2 form, this is also important for the Cayley manifold and Cayley geometry. You can construct these form. One form, omega xy, is nothing but actually jx. Take the orthogonal part of x, multiply with y. If you look at that, this form, it's more or less the same idea. This the orthogonal part and the arbitrary v. So for the analog of the Cayley-2 form is actually defined with the Cayley-4 form. As you remember that you can construct the Cayley manifold with the Cayley-2 form. So the same idea, you can construct spin 7 geometry with the Cayley-4 form. Okay, and how do we construct the Cayley manifold? If you have these kinds of you remember maybe, but if not, no problem, I will write. If you have these kinds of form, and the Cayley manifold says that the definition of Cayley manifold, I will say later, dV has to equal to 0, okay, and this is alternating form, and the complete plane, this has to be preserved, okay, dV equal to 0, either V equal to 0, one of them has to satisfy, or the complex structure has to be parallel. This is the definition of Cayley, but if you look at that, the spin 7 geometry, this is analog. So again, the phi 0 has to be equal to 0, or the gray also maybe Fernandez, I confused all directional derivative has to be 0, okay, and there's no other new information because they are interrelated to each other directly. We can construct, and this is the analog of Kähler geometry, and the importance of this geometry, spin 7 geometry and G2 geometry, maybe special Lagrangian, coming from the Harvey Lawson 1982 article. This article gave a new direction to minimal submanifold. So actually, the previously minimal submanifold generally defined on R3, and that R3 somehow the theory works as the calculating the mean curvature, calculating the also solving the PDE equation, finding a minimal submanifold. Actually, that part is using the PDE theoretic methods and also some geometric construction. But after this, the calibration theory, calibrated geometry, Harvey and Lawson changed the direction. Actually, the calibrated manifolds, submanifolds, are the special kind of minimal submanifold. Okay, we guarantee that the calibrated submanifolds are the minimal submanifolds of a Riemannian manifold. If you have a spatial closed form, I mean, I mentioned just a couple minutes ago. Here, this is the closed form. Okay, so analog of these spaces is the d phi. Also, you have to choose the closed form. Okay, for closed form, and for G2, we can say that the analog, the associative and the co-associative forms, both of them has to be closed. And at that situation, you can define the calibrated submanifold at this theory. Okay, so this is the minimal submanifold, and new types of submanifolds and construction can be useful for higher dimension. And in the next week, on the deeply parts of the minimal submanifolds, probably Mustafa shows us about the minimal submanifold theory. Maybe in the next week you can wait a little bit, but today we will continue from the calibration part. Okay, and just we are studying on the spatial kind of minimal submanifold, not a general theory. And what's the meaning of the calibration? Here, the calibration is actually if you have a differential K form. So differential K form defines the calibration on your manifolds. Okay, so if you have phi as a K form, and if it's closed, okay, the phi equal to 0, and if you restrict any spaces phi to V, okay, K plane, and if this restriction gives us the alpha times volume V, okay, but here our phi restricted to V is smaller than volume V if alpha smaller than 1. Okay, this name by the calibration. Okay, so we need two information. One of them is closeness, okay? And another one is the phi V equal to alpha times volume V, and this alpha has to be smaller than or equal to 1. Again, if you know some Kähler geometry, you can see that this is again the direct analog of this part, and the complex spaces. If you have the Kähler form, the closed form, and this Kähler form satisfy the Wirtinger inequality, and it has to be smaller than or equal to 1. You can find such spatial form. Again, we will change the form. Okay, but the importance of this theory, you can find a new types of minimal submanifolds. And for all k-dimensional spaces seen as the Grassmannian manifold here, for k-dimensional subspace of Rn, you can see the Grassmannian manifold. What's the meaning of the Grassmannian manifold? Actually, very simple cases you can see in a higher dimension. It's not so simple, but you feel from, for instance, G1 R3, okay, the orientable one. This plus means orientable one. You don't need to take both of them. In R3, if you take the one-dimensional spaces, now we are living in a three-dimensional object. For three-dimensional object, for each direction, you have a vector, okay? So this vector is a one-dimensional object. You can think about two-dimensional this is orientable, so you don't need the other. And for vectors, you can take the and then a point on a sphere, so we get and the same idea. If you are thinking about that the two-dimensional plane in R2, so for two-dimensional vector spaces, can be thought as the plane. So for each plane in R2 can be defined with a normal vector. So actually, for this normal vector can be seen as, I mean, for each vector you can define the plane. So these are isomorphic, okay, and exactly the same. For each vector you can define a plane vector. So the plane, and for this plane you can construct the normal vector. For this normal vector can be seen as a G1R3, okay, directly. And so if you understand the Grassmannian, for these Grassmannian spaces, Grassmannian manifold is defined a manifold also. The k-dimensional subspaces, you can think about that the vector, okay, from here autonomous frame, E1 to EK, all possible k-dimensional option, and phi be a k form on Rn. If the phi is 0, so this means that the phi is closed, and phi v1 to vk smaller than 1. This is another definition of the being the calibrated manifold here. So the same as this picture, okay? This definition, same idea. You can use this phi is closed, and if phi eats the v1 to vk, now we will find the real numbers, right? Then we can say that phi v1 to vk has to be smaller than 1. So this is the correspondence of the second requirement. We can say that phi is called the calibration on Rn. So now we pass the plane, calibrated plane, or the minimal submanifold. If you have the manifold, the larger manifold, and this space, the calibrated, I mean, if you have the phi is a calibration, okay, satisfy the 1 and smaller than 1. If phi restricted to V, and if it is equal to volume V, okay, then V is called a calibrated plane or a phi plane. And The set of all 5 planes are the contact space, the contact set. This contact set, I mean, don't confuse the contact geometry. This is for the Grassmannian. If you pick a point, for each point you will put a plane. So this is named by the contact part, because for each point there's a connection between these points, and that's why it's named by the contact set. And here we can see some example. If you are in a Kähler manifold, and the Kähler manifold, you remember I said this is the smaller than 1, and this theory of this not smaller than or equal to 1. This Kähler form is named by this equality, Wirtinger inequality. Okay, and calibrated planes. This is the minimal plane. Okay, minimal submanifold. So this is the complex plane, and here now the new parts, the Calabi-Yau manifold. For this Calabi-Yau manifold, if you define the holomorphic volume form, this holomorphic volume form, if you take the real parts of this omega, it's gonna be as a submanifold spatial Lagrangian M-planes here. And also we studied at these places from Mustafa the subplanes of G3 are 6. This is also very important for the string theory or M theory, because the Calabi-Yau, I said that the 10-dimensional object from string theory, 4 is the observable Minkowski space, and 6 is the invisible geometry or hidden dimension for the 10-dimensional string theory, and that's why 6 is important. And we checked that the 3-dimensional subplanes of this 6-dimensional object, and this space is the spatial Lagrangian M-planes spaces, and you can look at that the Calabi-Yau manifold into 2 parts. One of them is, you can start with the fixed Calabi-Yau manifold, and you can try to understand the spatial Lagrangian M-planes. Or another way is that if you can think about that, the all typical Calabi-Yau manifolds, G3 are 6. At the end of the day, you can look at the all possible spatial Lagrangian. So these spaces sitting inside of the G3 R6. Okay, and the bigger spaces, for each element defines a spatial Lagrangian. So the properties of this spatial Lagrangian has also important, and we studied on this one. Again, I said that hyperkähler manifold, and here in 3 different directions we have the Kähler manifolds, and that's why it's named by the hyperkähler. For these 5, if you calculate the submanifold or restricted form phi, you will find the quaternion lines. And G2 is the image of octanions have 2 different types of the submanifold. One of them is associative triplanes, one of them is co-associative triplanes. G2 defined with phi, and this phi is restrict submanifold. Okay, and this submanifold is somehow minimal submanifold. That's important. Spin 7 manifold is also another calibrated geometry calibration defined with a phi, and here or C, whatever you want. Important part is the name. It's the Kähler form. So if you have Cayley-4 form. So Harvey and Lawson papers showed that Cayley-4 form is the minimal submanifold. Okay? This is the non-trivial example for this new direction here. So the fundamental theorem of calibration is not so complicated. If phi is the calibration, calibration means we write d phi equal to 0 and phi restricted to v has to be smaller than alpha times another phi z, and this alpha smaller than sorry, not 0, smaller than 1. This defines a calibration here. And here the theory is n is a compact calibrated submanifold of M. Okay, so n is a volume minimizing in this homology class. The homology classes means, if you don't know this one, it's not so important, but here think about that we have choose the boundary about this homology class. Let's say the boundary of n. Boundary of n here. So you can define the n somewhere here. I can use maybe different color. So like this. Okay, this is our manifolds. And we can define another manifold at this boundary. Okay, I mean you can shrink a little bit. Okay. I don't know. I can feel, but here this is the boundary. This is one of them, M prime. The red one. This one is N or N1. The red one N2. And third one N3, whatever. But here we guaranteed that N is of new spaces. The same thing, let's say the N. N is volume minimizing, so if you have this type of boundary, N is the smallest one. Okay, you shrink your surfaces. If you think about that, the surface got theory available for any dimensional object. Your theorem says that if you have a calibration and n is your calibrated submanifold, so calibrated submanifold means you have a phi restricted to n, you will calculate on n, it will give us 1. So this n is just the smallest one. Okay, there are lots of different n for these, like a bubble. I mean, it's enlarge or shrink, larger or greater different elements. The same homology classes means, I mean, you can element change without any hole, without any pinching, but the theory says that at these points, n is, if calibrated submanifold, it has to be volume minimizing. I mean, you can choose the different submanifold here, and if phi is restricted to n equal to 1, Harvey and Lawson says that n has to be volume minimizing. The proof is so easy, but finding these types of example is a little bit harder. let's say we have N is a compact calibrated manifold. Calibrated means it's equal to 1 if you restrict these spaces. And the same homology classes take the M prime such that N and M prime equal in the P dimension. Okay, so we know that the volume of N you can calculate phi and N. Okay, phi is restricted to N actually, and you can calculate it from phi to N. We can find the volume of N here, and Stokes theorem says that if they are equal, I mean, there's no boundary. You can think about that. This is N. Here, this one, let's say M prime, and this is just N. Okay, not a good picture to be able to understand, but maybe I can erase and I can try. This one is the assume this is boundary, and because of the homology, this one is M prime and this one is N. Okay, so if you reverse the orientation, N minus N, okay, boundary is 0, right? This is the closed, the compact object, and from the Stokes theorem, you can write that here actually the theory is like this actually: N minus M prime phi. There's no boundary. Okay, that's why the Stokes theorem works. There's no boundary. It's equal to 0 actually, and from here you can write that N equal to M prime on this phi. But we know that M prime phi is not now for this geometry. We wrote that as a definition smaller than or equal to volume M prime. You remember alpha times volume M prime, and alpha has to be smaller than 1. So it's directly says that M prime phi has to be smaller than M prime, and so we can say that for all N has to be smaller than other possible M prime. Okay? This one is the crucial point of our theory, because at the starting we say that at the beginning we said that for each other submanifold smaller than or equal to volume of N, and then directly we can say that volume N smaller than volume M prime. And okay, we constructed the calibrated geometry and some information related to submanifold. We are trying to understand the G structure. So if you have the manifolds, and for these manifolds, you can construct the structure from the structural group of the tangent bundle. For our manifold, you can maybe you can remember the manifold theory or the definition of manifold somehow. For each point, you can find the set from the Rn to Rn, okay? And for the intersection part, you can define an element or overlap function, and this function is the element of GLN, and this is named by the structural group actually, and the structural group of Tm can be topologically reduced from GLN to G, and so this the tangent bundle named by M has the topological G structure. I mean, if you choose the specific G, so what's that? If your structural group or N, so you can define the Riemannian metric, but if G is smaller than to ON, this means that SON, and you can construct the orientable Riemannian metric. Okay, and then one step further, we will see that the spin structure, if you have a spin structure, this means that your space has two different directions in at one point. Okay, this is roughly speaking of the spin structure. So spin structure is the cover of SO2. So for each SON, for each element of SON, okay, you will find the spin n. For each point, we have two different sheet actually, and this is the covering spaces is the mathematical object, but the spin part induced from physics actually. The experiments of Stern-Gerlach for each particle has a spin structure. It's the scattering in the screen. Maybe you can see into two different pieces for each of them. So for each particle have the spin structure, and it depends. You know, the physical background is not so good for me, but for each spaces, each particle, some of them not, some of them has the spin structure. Some particle have the spin particle, so it has the spin structure separated into two pieces. So somehow we have to define this one as a mathematically. And if you have the rotation, so for this rotation you have two different rotation at before the experiment. It's related with the quantum theory, I guess. So the spin structure is this one. If we have the manifold, so our structure group, the manifold structure group overlapping. If you have a double cover, okay, we can say that M admits a spin structure, and this one is this part is the theory related to the characteristic class theory. You can show that if M has a spin structure on a tangent bundle, actually, V1 M and V2 M equal to 0. So V1, if V1 equal to 0, this space is orientable space, and also V2 equal to 0, we can say that our M has a spin structure. V1 and V2 Stiefel-Whitney classes. So these classes are, I said, how do we glue your tangent bundle with respect to your manifold? So a little bit some topological information. The gluing your bundles, the direction of the gluing bundle gives us the first, third, I mean, with respect to dimension, gives us the Stiefel-Whitney classes. It's just the element form. I mean, you have two different orientation. Either you can glue directly or reverse direction. So the element form Stiefel-Whitney classes for each class is just 1 or Z2. Okay, from element 0 or 1. But to be able to understand a little bit complicated, maybe you can check the Stashev books, Miller and Stashev characteristic classes book. Characteristic classes. Stashev. Many better book maybe, but this is the classical book to suggest for everyone. And if the tangent bundle admits the spin structure and V1 and V2 equal to 0, we can say the remaining manifold is the spin manifold. And the spin 7 structure is a little bit powerful if you compare the spin structure. So at first, the spin 7 structure is element of SO8. So at first, M has to be spin. Spin means actually, I mean, if you are talking about the 8-dimensional object, for 8-dimensional object, the spin 7 is not our coverage yet. At first, we have to check that M8 is spin means V1 and V2 equal to 0, or this manifold is a Riemannian orientable manifold SO8, and at first you have to find the spin 8, okay? Because we are living in an 8-dimensional the 8-dimensional object, and this object has to the structural group is the element of SO8, and if it has the spin 7, if it has a spin structure, so this means that we have a spin 8 double cover of SO8. Okay, so M has to be spin structure. If you can reduce your structural group into spin 7, shrink your group into a smaller group, we can say that M has the spin 7 structure. Okay, this structure is the powerful, more powerful than the spin 8 structure. At first, M8 has to be spin, then it has to be it will check. It will be checked the spin 8 spin 7 condition. So actually, spin 7 is the narrow group if you compare the spin 8. Okay, and the Harvey and Lobson gives us a direction about this spin 7 geometry, and spin 7 structure at first V1 and V2 equal to 0, so this means that being a spin structure, and then if you have P1 and P2 and the other class of M, if you have the equality P1 M square and for P2 M, this is a Pontryagin class. Okay. And it's equal to 0. So for this 8-dimension Pontryagin class is the it's for vector actually. P1 square eats the 8-dimensional object. So P2 is again 8-dimension, and Euler class is the top class, so it has to eat 8-dimensional object. And for this equality holds, we can say that M has the spin 7 structure. Okay, so here, as I said at the beginning, if you choose M and N compact spin for manifolds for our construction, you can start with, I mean, not an 8-dimensional object. You can start with the 2 4-dimensional object. Your holonomy reduced. We know that it's inside of this, the holonomy is equal to spin 7, but inside of the holonomy, not a full holonomy. This means that there are lots of subgroup of spin 7. Here, one of them. If you separate your spaces into 2-piece 4-dimensional object, you can find again the spin 7 structure at X equal to M cross N. The restriction again from here, this sigma is a signature of your spaces. This is the Euler characteristic, again the Euler class of your spaces, and if you choose M cross M, you can find this equality, your spaces, okay, to be able to construct spin 7 structure. The trivial one actually for the spin 7 are 8. That's what are 8. Okay, and you have the 4 form, and this 4 form actually directly defined here. This is the real long form, but if you use this form for R8 directly, okay, this is nothing but bx1 wedge dx2 wedge dx3 wedge dx4, okay, and this is the standard Cayley form, and R8 combining with this 5 directly define the spin 7 structure. Okay, but this is a very trivial example and starting point. But we wonder, can we find that the correspondence element for this spin 7 structure for any arbitrary 8-dimensional object? Because we talked about before, R8 is very simple, and you can define the 4-dimensional object. Directly you can see, but we want to generalize this information into arbitrary 8-dimensional object, because life is not so simple. We can get simpler, but the starting is R8. You are right, but we want to generalize this information from here, and R8 is the first example of our spin 7 geometry. If you think about that phi 0, this phi 0 gives us the Cayley form, and this Cayley form, don't confuse Cayley. Cayley form gives us the Cayley submanifold, and this submanifold is also the minimal submanifold. Okay, and another example, the K3 surface. Again, this is a little bit algebraic notion, but for this theory, the trunk class of our spaces can be seen as if, by the way, the Pontryagin class is a 4-dimensional classes, each 4-dimensional object, but if you have the on the complex spaces, complex manifold, your Pontryagin class can be seen as a combination of a trunk class defined in a complex manifold, okay, and defined with a Hermitian manifold. And from here, if V and D and D is a degree and is a dimension, these types of surface and the Chern class defined with this element. From here, we can see that V and D, the 4-dimensional object, is spin. At first, we have to satisfy the spin, and M plus D, it's equal to even, and then so V2,4 is the elements of CP3. If you multiply, if you take the product of this 4-dimensional object, it admits the spin 7 structure. I mean, this one is a non-trivial. Again, it's simple because we separated your 8-dimensional object into 4-dimensional object, but this is at least one of them, the non-trivial example. So maybe yes. After that, after this point, we will continue the complex manifold and Cayley manifold, and also Calabi-Yau manifold. The core of this talk, maybe we can leave at Friday. Mustafa, is it okay? We can finish here.
Okay.
Everything okay?
Thank you very much. Yeah, we can continue with that one.
Mhm. Okay, thank you so much. If you have any question, please let me know.
Any questions?
Thank you.
Okay. So thanks for the speaker